Microsoft have just announced the Majorana 1 chip, the world's first topological qubit, and it's gotten kind of a lot of attention. But unlike normal quantum computers, Microsoft's chip doesn't use the quantum states of localized atoms, ions, or photons. It stores quantum information across a surface or topology, making it resilient to the noise that currently limits quantum computation and potentially finally giving us a viable, scalable way to realize a quantum computer. And you know, it's kind of going to be a wild video when I have to start with in normal quantum computers. As part of this breakthrough announcement, Microsoft gave me exclusive access to some of the key team members behind the breakthrough to try and better understand what is exactly going on here and how big of a deal this really could be.
We had to essentially invent a new state of matter.
But my words and my opinions are my own. I want to understand, how does this new approach to quantum work, why is it potentially so powerful, and what does it unlock for us? I want to explain why I think it's a big deal, what the Majorana 1 chip means, but also what it doesn't mean. And I'd really like an answer as to why the word Majorana makes me question my ability to read and write. Let's start with the easy stuff. How to build an impossible computer using laws of the universe we don't fully understand with a particle we don't know how to pronounce. Let's dive in.
For the first time ever, our computer lab actually has a computer in it.
Quantum computers promise something extraordinary, computing power that could one day outstrip the most powerful supercomputers on the planet, that could revolutionize material science, drug discovery, and optimization problems that are practically impossible for classical computers to solve. But there is one big problem. Noise. Quantum computers today are incredibly fragile. The very thing that makes them powerful, quantum mechanics, is also what makes them difficult to control. To understand why they break so easily, we have to understand that measuring a qubit, which can be 0, 1, or somewhere in between, involves looking at it. Either we shine a light on it, apply an electric or magnetic field to it, or we use some other interaction to extract information. But the very act of measurement disturbs the system, and we say collapses the wave function. That means it stops being a blend of 0 and 1 and settles into being one or the other. The problem comes when this observation happens midway through our computation. If a stray photon, a minor temperature fluctuation, or even a vibration at the atomic level, any of these can collapse the qubit state prematurely, called decoherence, and the quantum computation is lost. That is why, around all quantum computers, we see this shrouding on the outside of an otherwise very shiny setup straight out of sci-fi fantasy. It does a few things. It creates a vacuum chamber in which all air can be pumped out of so no stray atoms can bump into and interrupt a quantum computation. It also allows the system to be cooled down to about 50 millikelvin. That's just 0.05 degrees above absolute zero. This temperature, not even the atoms move. In comparison, deep space, the space between the stars, is a balmy 2.7 Kelvin, or compared to Antarctica's coldest recorded temperature of 184 Kelvin, or minus 88 degrees Celsius, well, this thing is just really, really cold. The shrouding also shields against electromagnetism, light, RF frequencies from your phone antenna, any magnetic field or signals that may influence the system, all in an attempt to keep this quantum state preserved. But at the moment, it still isn't enough.
A quasi-particle from outside is just going to disturb the state in a second, it's all gone. You're already running at 50 millikelvin or something, super low temperatures, but you're still not in a regime where you can manipulate the device successfully.
Qubits are still exceptionally delicate and cause computation-destroying errors, and unless we solve this issue, quantum computers may never reach their potential. Now here you might be thinking, well, why not just fix those errors? After all, in classical computers, we have error correction built in. If a bit flips due to electrical noise, redundancies in the system catch it and correct it, or at the very least it helps you set a speed record in Mario. But quantum error correction is a completely different challenge. Because of the no cloning theorem, you can't just copy qubits like you would classical bits. Instead, quantum computers use a process called quantum error correction codes, where multiple physical qubits work together to form a single, more stable, logical qubit. These error correction schemes require a huge amount of redundancy. In today's leading quantum systems, like superconducting qubits, one logical qubit might require hundreds or even thousands of physical qubits just to keep it stable. So to build a full quantum computer with just 1,000 logical qubits, you'd actually need millions of physical qubits just to make it work. And this isn't just an inconvenience, this is a fundamental barrier to scaling quantum computers. You are looking at a useful quantum computer that needs to be the size of a football stadium. But what if instead of constantly fighting against the noise, you could design a system where noise simply didn't matter as much? A system where the quantum information was protected not by redundancy, but by the very nature of physics itself. As Chetan Nayak from Microsoft explained to me,
needed something in which the quantum mechanical wave functions would have some underlying kind of rigidity that would protect them from errors, because they ordinarily are pretty delicate.
This is where Microsoft are taking a fundamentally different approach. Topology studies properties of spaces that are invariant or unchanging under any continuous deformation. Now, admittedly, that's kind of a bit of a mouthful, so let's think about it in terms of a simple example. If you take a rope and tie a knot into that rope, you can do many different things to that rope and the knot will stay essentially the same. You could move it, shake it, pull it up and down, bend it slightly. There is still fundamentally one knot in that rope. You'd have to do something reasonably dramatic like cutting it, which I'm not going to do because this is my shoelace, in order to actually destroy it. That is the idea behind topological quantum computing. It weaves quantum information into a global property that is fundamental to that system, and as a result, it becomes naturally immune to small errors.
So what we are doing is something fundamentally different. We are saying, hey, first step is get hardware protection built in at the ground level. And so if you take the quantum information and you distribute it, now that information is much more resilient to being displaced and destroyed, even if it sees events or noise from outside sources.
But to actually realize a topological quantum computer, we're going to need a new way of thinking about how we do computation. And we're going to need one of the strangest objects in quantum mechanics, the Majorana particle.
That's the same computer astronauts use to do their taxes.
The Majorana particle was proposed by Ettore Majorana, an Italian physicist working in quantum and nuclear physics at a time when the world was on the brink of world war. He was considered one of the greatest minds of his time, often compared to Einstein or Dirac, but he had a fascinating reluctance to publishing his work, considering his discoveries too trivial to be worth discussing. Majorana's Majorana, kind of confusing, was always proposed to be found in pairs. But unlike all other particles which have an antiparticle in existence, the electron with the positron, the proton with the antiproton, each with equal and opposite charge that annihilate each other when they touch, a Majorana particle would be its own antiparticle. Strangely, Majorana never expanded much on this work. That's because in March of 1938, he boarded a boat in Palmero, bound for Naples, carrying papers containing many such revolutionary ideas. But when the boat arrived in Naples, Majorana wasn't on it. He had simply disappeared, and was never seen of or heard from ever again. Potentially, he found his own antiparticle. For decades, physicists searched for Majorana particles in high-energy physics, particularly in neutrinos, hoping to prove that the ghostly particles were their own antiparticles. The breakthrough, however, never arrived for high-energy physics. Instead, it came from condensed matter. In 2012, researchers at Delft University showed that in a small nanowire created from a combination of semiconductor and superconducting layers, and exactly the right conditions, Majorana-like behaviors suddenly arose. And when I say suddenly arose, actually putting this thing together and getting it to operate is unbelievably complicated. It's taken Microsoft the last 17 years to get it right, and there are a lot of false starts along the way.
I often tell my team, this is not science. This is science and art. Because the whole idea here is, how do we build a crystal structure that is so perfect? Every single atom has to be placed perfectly where it needs to be.
Here's a quick screen grab of some of those results from a video by Domain of Science that I'll link in the description down below that shows the astonishing level of atomic accuracy within this material, with literally not a single atom out of place. But how does this proposed nanowire actually work? The wire is produced from a semiconductor material that contains mobile electrons, much like any other semiconductor. These electrons move freely and can be controlled by electric field gates to move electrons in and out of the wire. On top of this semiconductor nanowire, a thin layer of superconductor is deposited. By cooling the nanowire down to 50 millikelvin, necessary for quantum computation, the superconductor also enters a superconducting state, where electrons can move up and down its length with zero resistance, moderated by Cooper pairs, pairs of electrons that move freely within a superconductor. The strange part is that some of these Cooper pairs can tunnel into the semiconductor nanowire below, and allow the semiconductor to borrow borrow some of the superconducting properties through a process called proximity effect. Then when a strong magnetic field is applied, the electronic states within the nanowire do something even stranger. They split into two separate quantum states that exist at either of the boundary ends of the nanowire, the two Majorana particles we have been searching for, each their own antiparticle. What this means is that the information about the electrons on these wires is now spread across the length of the wire. And as weird as this kind of sounds, you can think about it as each electron in the wire existing at both ends of the wire at the same time, or half an electron at this end and half an electron at the other. Microsoft are referring to this as a topoconductor and describing it as a new state of matter. I think this is broadly a fair statement. We know about solids, liquids, gases, but it's also worth knowing that there are about 20 total states of matter, like plasmas, Bose-Einstein condensates, superfluids. I think, though, this fairly earns its place as a new state of matter. But my question was, how do we actually make a quantum computer out of this? To build a qubit, you always need two distinguishable states. You can use polarization direction of light or the spin of a trapped ion, but here we use the number of electrons on the nanowire. Across the wire, there will either be an even number, which we could call 0, or an odd number, which we could call 1. If the electrons were happily sitting on a normal wire, it would be very possible for a photon particle or other interaction to knock one of them off or to add another one, and so change the parity of this system. This ultimately would collapse the wave function and break any usefulness it had to us for computation. The Majorana zero modes, however, change this electron information and cause it to be distributed across the length of the wire so that it is no longer localized in individual electrons, but each electron's information is now spread across the wire's full length, concentrated at either end. This means that if some external noise disturbs one end of the system, it doesn't immediately destroy the quantum state, and this gives us the world's first topological quantum qubit.
You're back to your computational basics using a particle, a quasi-particle, that has never been captured before.
This makes Majorana-based qubits naturally resistant to small errors, unlike traditional superconducting or trapped ion qubits, which need extensive error correction to stay stable. And this really is what everyone is so excited about, and why Majorana zero modes are such a big deal. If we can use them to build qubits, we might not need those massive error correction overheads. Instead, the hardware itself would provide built-in fault tolerance, and for the first time we wouldn't need a football stadium of qubits to correct for those errors. Up until now, the quantum race has always been about quantity. How can we get more qubits in our system? Microsoft have been way behind in this race, but instead of focusing on quantity, they have put their efforts into quality. As a result, they are changing the rules of this game and creating a new quantum system that is inherently stable. So when they do start scaling, each qubit will count for a lot more.
So we not only demonstrated it, we captured it, we control it, and now we are able to do it repeatably, and we have built an array out of it.
As an output of all this work, Microsoft have built the Majorana 1. This is an 8-qubit chip, so a proof of concept chip, where they have detected, controlled, and read out from these Majorana qubits for the very first time.
It's going to be an inflection point for this industry. I mean, we are tremendously excited of what we are going to do with this thing.
Now, this might not sound huge in terms of number, but this architecture now makes it realistic to build a large number of stable qubits in a single place, all fabricated on a chip that you could actually hold in your hand. Yes, it will still need to sit into the normal quantum computing steampunk chandelier, but this is a potential huge step forwards. So the next step for Microsoft is to scale this chip from 8 qubits to 1,000,000 qubits, which yes, does kind of sound like a huge leap, but when I asked about how long it would take, I was kind of surprised by their answer.
Some people have said useful quantum computers are decades away. I think it's years.
Before now, we've talked about the possibility of functional quantum computers being optimistically a decade, if not more, away. So a few years seems like a huge announcement. Zulfi explained that the reason for this step change is that they are no longer in a fundamental science space, but now this is moving to be an engineering problem.
We are on to something big here. It essentially changes the timeline, because once it becomes more engineering and less reinventing the science, it becomes less, hey, I have these 5 miracles to cross before I can do this. There's no more miracle requirement. It's more about the appropriate engineering rigor, predictability, and setting out very clear goals in front of us.
So if reliably engineered quantum computers are only 3 years away, again, I'm being slightly optimistic here, it begs the question of will they finally be able to run Crisis on max settings? No, it begs the question of what are we actually going to do with them?
We want you to tell us the answer.
The answer to what?
From solving climate change to curing cancer, there are some lofty ambitions for where quantum computing could actually take us. But while these might be long-term goals, I don't often come across practical explanations of how or why quantum computers will actually be useful to us. So this is exactly what I posed to Nathan Baker, head of Microsoft Quantum Applications team.
The short answer is chemistry. I think the long answer is what are you going to do differently in chemistry? And I think that's the spirit of your question. What is quantum going to enable us to do? So chemistry is all about change, right? A chemical reaction is about making or breaking new bonds. And the way we think about how fast reactions occur, those bond making and breaking processes, is by looking at something called an energy landscape.
The ease or difficulty of getting chemicals to interact, bond, or destroy other materials is dependent on the energy requirement to make that change. You can think of this almost like a hill or a barrier that a chemical needs to overcome in order to do its job. The higher the hill, the harder the task, but also the slower the rate of this process.
Energy barriers, the height of those hills, are super sensitive to the accuracy of the calculation. And, quantum mechanics is hard. It's not just hard for people, it's hard for classical computers.
Today we do the best job that we can with classical computers, but with big systems, classical computers just can't keep up. We have to make approximations and it impacts our accuracy.
Yeah, conventional wisdom, and this is conventional wisdom backed by a lot of studies, says that when a molecule has about 23, 24 orbitals in it, again, that's where these electrons can be around the molecule. The system gets really hard for a classical computer, too hard for a classical computer to solve it. And honestly, you can hit that number of orbitals for very, very small systems. One of the simplest chemical reactions received a Nobel Prize a few decades ago is the interaction of ozone with chlorine in the environment. You can model that very simply, fit it onto a classical computer, but if you want to model the full complexity of that system, you're already in a space where you have to make approximations on the classical computer, but the quantum computer can start to solve it very naturally.
The reality is that right now, when we try and model some of these chemical reactions, we can be thousands of fold off in our accuracy, which means there's a lot of guess and check involved in predicting new and useful chemicals and catalysts.
Imagine if you're trying to understand what happens to a chemical in the environment. Well, when it gets in the environment, it starts reacting with oxygen, ozone, other things in the environment, and the speed of that reaction is determined by those energy barriers. A small error in that energy barrier is the difference between a chemical that goes away immediately and a forever chemical.
But with a quantum computer, that changes. Quantum computers will allow us to predict and model chemicals at the quantum scale, determining exactly how their electrons are interacting and the energy requirements necessary to make them catalyze or react. If we can move our approximations into a quantum computer, it may give us the ability to be first time right with the computations that we're doing, discovering chemicals that definitively work. Potentially, and that's a big potentially, we are on the cusp of a new quantum age. Now is the time to really start thinking about the questions that we want to ask of this new quantum universe. But before we get too carried away, let's talk about the controversy.
Must have been hard debugging all those computers, Homer?
Absolutely.
In all new breakthroughs, there is always some controversy, deserved or not, and I want to touch briefly on this just to tell the complete story here. As exciting as this sounds, not everyone is convinced, and that skepticism isn't just a knee-jerk reaction, it is built into the history of quantum computing. Microsoft itself published a high-profile paper back in 2018 to have claimed to have observed Majorana zero modes in their system, but in 2021, independent researchers found flaws in their data analysis and the paper was retracted. It was a major setback, but Microsoft isn't alone. Across the industry, we've seen big leaps forward followed by unexpected complications. This time, Microsoft says they've addressed past issues and have new evidence of the Majorana zero mode forming in their Majorana 1 chip. Their new paper claims to have overcome these previous misinterpretations, presenting what they describe as the clearest path yet to scalable quantum computers. But some physicists aren't convinced. The concern is the disconnect between the scientific article and the public claims that have been made. The most obvious one that has the physics community kind of riled up is that the Nature paper just released doesn't actually provide empirical evidence of a topological qubit. The editors even took the rare step of highlighting this at the top of the paper, and this omission has just been a point of discussion, as measurements like coherence times are essential for assessing the practical viability of qubits in computational tasks. In a comment from Chaitan on Scott Arson's blog, he explains that Microsoft's Nature paper was submitted about a year ago in March of 2024 and only published this month, and that Microsoft have made significant progress in that intervening year, the results of which he discussed at a recent conference, and that this time do show parity measurement and qubit function. This work was also presented at Station Q prior to the announcement, and there are talks scheduled for the upcoming APS meeting. Now, taking a step back with my I run a venture capital fund hat on that invests specifically in these sorts of breakthroughs, a red flag does ping in my mind around the loudness of the release versus the timings with the Nature paper that don't quite validate this announcement. But also, that paper releases are very slow activities, and they won't always necessarily align with the news that you want to report as a venture. That skepticism is healthy, that's science, but so is that excitement if Microsoft are correct, that they have found a way to make qubits that are exponentially more robust than anything we've ever seen before. If that is right, that is one of the most exciting breakthroughs that we've had not just in science, but in the history of humanity. And to me, science is humanity's defining characteristic. We like to think of ourselves as unique, the pinnacle of intelligence, the only creatures to wield tools to create art, to communicate with language, to build societies. But we have seen chimpanzees fashion spears, and crows craft hooks to fish for prey. We've even seen buffalo vote on which direction to travel, and dolphins call each other by name. And yet, there remains one singular act of defiance of our universe that is ours alone. No other being devises instruments to understand reality, to see the unseeable and touch the untouchable. We are defined by our willingness to challenge the universe's limits, to look at the deep chaotic complexity of the cosmos and whisper, that seems impossible. I bet we could do it. To me, that is always worth celebrating. If you liked this video, leave a like or a comment down below. For members of the channel, I'll be releasing the full interviews I did with Zulfi, Chaitan, and Nathan, which are all super interesting. Thank you so much to Microsoft for giving me access and opportunity to tell this amazing story. If you like science and tech breakthroughs, follow for more. Until then, I'll see you next week. Goodbye.